Okay, so today's discussion is on chapter 8, total differential. Again, you can check the chapter on Chang and Reinhardt's book, again on chapter 8. Okay, we'll first start with this given function. So supposing that y is a function of x sub 1 and x sub 2. Now, when we talk about total differential class, or on our discussion in chapter 7, talks about partial derivatives, right? So in partial derivatives class, we allow one variable to change and we're holding other things constant. So again, when we talk about partial derivative, again, we're taking it with respect to x sub 1 and also taking it with respect to x sub 2. So the change is, again, when you talk about delta or you talk about changes in these variables, it is only here, okay? So it's only a change in, it's only delta x sub 1 and it's also delta x sub 2. Ang nangyayari, or when you talk about total differential, it now is a change in y itself. Okay, so again, partial derivatives, you talk about the changes in any of these variables, x sub 1 and x sub 2. When you talk about total differential class, it talks about the change here in the dependent variable. So again, it's delta y, that's dy here, or that is the change in, again, the total change in your dependent. So again, that is the difference between total differential and that of partial derivatives. Okay, so partial derivatives dito, and when you talk about total differential, again, you talk about the total change here in your dependent variable. Okay, so by definition, class, again, by definition, dy dx is just, again, the limit when when delta x approaches to 0. So you can see here that when we talk about dy dx, again, you can think of it as ratios. So again, the difference of this, let me just go into that one. So when you talk about dy dx, class, again, it is just an approximation, and you can interpret dy dx as just, again, two quantities, or the ratio of two quantities, dy and dx. So just to summarize again the whole point of what total differential is, again, it is just getting the total change, okay, total change on the dependent variable. Now, but again, going back to our function here, so when we have a linear function, y is a function of x sub 1, x sub 2, getting the total change, or getting the, getting total differential of this function here would mean that you need first to get the partial derivative with respect to x sub 1 multiplied by the change of x sub 1 plus partial derivative with respect to x sub 2 times the change in x sub 2. Okay, so again, when you are getting total differential, you're getting the I actually keep on repeating this one, but again, this is important. That is getting the total change that is on your dependent variable. So that is, again, partial f, partial x sub 1 multiplied by the change in x sub 1 plus partial f, partial x sub 2 multiplied to the change of x sub 2. Okay, so I think this is better, class, when we have an example. So let's look into this one. So this is an exercise from an exercise from the chapter in the book. So suppose we have a function here. So z is a function of x of y, x and y. And so when we have these function here, z is equal to 3x squared plus xy minus 2y cubed. So let me just ask a few question, Gonzalez. When you have this function z, again, z is equal to 3x squared plus x sub xy minus 2y cubed, what do you think is the total differential, or what I don't think it's a formula. I cannot call it. How do we get generally the total differential of this function, Gonzalez? So if I ask you to get the total differential, again, without solving yet, this function here, how do we get total differential of z? Okay, so how about other hands class? How do we get total differential here? Jacinto?
Hello, ma'am.
Yes.
Kukuhain po yung derivative po nung lahat ng variable po.
Okay. Good, that's correct. But let me just add into that now. Let me rephrase that. So getting the total derivative getting the total differential of z would mean we're getting the first partial derivative. The first partial derivative with respect to x, and also the partial derivative with respect to y. So in that case, class, getting the total differential of z would be getting again the partial derivative with respect to x multiplied by the change in x here plus the partial derivative with respect to y multiplied by the change in y. So again, you can see that getting the total differential is just getting again this partial derivative and a change of x here. Quite also the same with when we have a function which is y is equal to a function of x of 1, x of 2. So technically, class, again, you just need to remember this one here when you're getting the total differential. So let's proceed. So Ferrer, when you're getting the because we already have our indication here of our indication here on getting the total differential of z, kindly go ahead and provide me this one here. So what's partial f partial x multiplied by dx here, Ferrer?
Ma'am, paulit na po.
Alright. Kindly supplement this one.
Partial f all over partial x is just equal to 6x plus y.
All right. Okay. Thank you. Okay. So, okay, thank you, Ferrer. So in that case, class, partial f partial x is just again 6x plus y times dx. Okay. How about you, Jacinto? What is partial f partial y?
Hello, ma'am.
Yes.
Partial.
What? Oh, okay. Let me go back to that. What's partial f partial y?
One minus 6y squared.
1. Again, that's partial y with respect to y.
Okay. 6y squared, ma'am.
Yes. That's 6y squared and okay. Yes. That's fine. But you're actually correct. But there's one lacking. Yes, Ferrer, you were raising your hand, I think.
The partial derivative of f all over partial derivative of y po is x minus 6y squared po.
Good, thank you. So again, getting the partial derivatives thus multiplied into the change in x and the change of y will have this one here. So it means that total derivative of z is just equal to 6x plus y multiplied by dx. Again, dx here is our change in x But in this case, we cannot get a value for dx, so we just get can carry on, or we just write it as dx plus the change plus x minus 6y squared multiplied by dy. So again, this is the total differential of z here. So again, total differential talks about the total change in your dependent variable. Okay, so let's talk about your utility function class. So as one of the applications for total differentials. Okay, so when you have this utility function, you know that utility is again you can get utility from a combination of these two goods, x sub 1 and x sub 2. Now, in consumer theory class, again, in consumer theory, we are concerned of we are concerned of two things. The first one is again the combination of these two goods that maximizes the utility of an individual, and the second one is that if we allow this one, or if there is a change, let's just say, let me put a bar here on the side. Bar. Okay. Sige, ito na lang. Okay, so and another thing is that if we hold utility constant now and we change our what would be the change, or if holding utility constant here and allowing a change in the combination of x sub 1 and x sub 2. So obviously, if there is a change, if we hold utility constant and we only again allow, because we're again staying in the same indifference curve here. Okay, right here. So again, going back to what I said, another thing, again, another consideration when we look at the utility function, if we're holding utility constant here, then how do we make changes in our combination of x sub 1, x sub 2, just to make the consumer just as happy as before, meaning to stay in the same indifference curve? Okay, so our agenda for today is again getting the marginal utilities of this utility function. So in that case, because marginal utility speaks of partial derivative with respect to x sub 1 and x sub 2, total differential tells us that if any of these changes, class, what would be that effect to the total, what would be the effect on the dependent variable. So again, very similar to our exercise earlier, getting total differential would mean that we can just type this one as, I'll just get this one to make it quicker. Okay, so getting the total differential of u here, or the total utility that we get from changing of any of these variables, would be equal to this one. Okay, so I'll just write this one down. So du, is that x sub 1? Okay, that's x sub 1. Okay. So it means to say that getting the total utility, or what's the total utility again from consuming another unit of these goods, would be equal to du. So again, du is our total utility, du is our total differential. And again, this is again, you're familiar with this one already. Du is partial u partial x sub 1 multiplied by dx sub 1 plus partial u partial x sub 2 dx sub 2. Now in this case, class, let me just do this one. Okay, in this case, class, what do we mean again by this one? Yes, Atiga, partial u partial x sub 1, we refer this one in consumer theory as what again? Right, okay, we have marginal utility of x. Very good. So in that case, class, again, what I have mentioned earlier, partial u partial x sub 1 is just your marginal utility of x, x sub 1. Okay, and in this case as well, partial u partial x sub 2 is again your marginal utility of x sub 2. So if you still remember, class, no, if you're so if you still remember, class, your indifference curve is just, or again, the slope of your indifference curve is just dy over dx, which means to say that this is a ratio of your marginal utilities, because your indifference curve is a downward sloping curve, meaning that the trade-offs, there is a trade-off, so your slope would be a negative. So dy over dx is again the slope of your indifference curve. That's the ratio of your marginal utility. So we can just rewrite this one as partial u partial, what is that again? Partial u partial x sub 1. Okay, so it would be we can rewrite the slope of the indifference curve similar to this one here. Okay, so it's a 2. Okay, so again, just getting from our function here, dy over dx is our slope, which means to say that it is just the ratio. Is it correct? Right. It is just the ratio of our marginal utilities, and our marginal utilities, class, is written this way, where we're getting the partial derivative with respect of these goods here. So that's partial u partial x sub 1 over partial u partial x sub 2. So which we can write in a compact way as this one. Okay, so I think you can still remember. I think you can find this one familiar to you. So that's mux and mu sub 1 sub 2. Okay, so again, getting or we can also say that the indifference curve is just your MRS, meaning your marginal rate of substitution. Okay, so right. So again, this slide right here, we're just extending our analysis or our discussion to the slope of the indifference curve. Okay, so what happens is that this is only when we are holding. This is only when we're holding our, especially when we're holding our utility constant. Okay, so if this is the case, class, if you're holding your utility constant, any of your changes here, or let me rephrase that one. If you know that you are staying in the same indifference curve, you want the consumer to be as happy as just before. I mean, just be the same, parang same happiness, same utility. Then and if you want to make trade-offs for this one, the total change in you, the total change in the dependent variable would be 0, because again, you are just making some trade-offs. Okay, you're just trying to parang perhaps consume more of x sub 2 and lessen your consumption of x sub 1. Okay, so but the thing here is that you are just holding utility constant. Okay, now let's have an example from the book, class. Supposing that we can change our utility here, it means that we are not holding utility or our dependent variable here as constant. Okay, so again, we are starting off with the utility function, which is again u is a function of x sub 1, x sub 2, and your utility function there is 2x sub 1 plus 9x sub 1 x sub 2 plus x2 squared. So let me call it some, yes, Kawano. What is the total differential of u here, or what's the total utility here?
For the partial derivative of x1, it's 2 plus 9x2. Then for the partial derivative of x2, it's 9x1 plus 2x.
Okay, let me just add before we continue. I'm still on partial u partial x sub 1. We need to add the x2 here, I mean the x1, because we're getting partial derivatives. I mean, we're getting the total differential. So it should, we should just add x sub d x sub 1. Okay, let me just add quickly. Okay, and then let's go to partial u partial x sub 2, Kawano. So please
Ano yung
proceed.
inad mo po, ma'am?
Yeah. Let me just, because we're getting the total differential, I'm adding dx sub 1.
Oh, okay.
Okay.
And then for the partial derivative of x2, it would be 9x1 plus 2x and dx2.
Yes, correct. Thank you. So I'll just catch up first. So that is 9 times 1 plus. Let me know if I'm correct. If I've written your answer correctly. So that's, what's that again? Okay. And then we have the okay. Is this correct, Kawano?
Yes, it's correct, ma'am.
All right, thank you. So again, class, you with again solving for the total differential u or the total when we allow again changes in our combinations of these two goods, what would be the total effect, or what would be again its effect on the dependent variable, which is again your total utility there. So the total differential is again du, that is 2 plus 9x sub 2, multiplied by again the change in x sub 1. Again, class, this is total differential, so you need to include the changes of your of these two these two variables. So that's dx1 plus 9x sub 1 plus 2x sub 2 multiplied by the change of your x sub 2, which is again dx sub 2 there. So what this means is that these first element here, or these again means here that this is our marginal utility of x sub 1 times the increment in the consumption of x sub 1. Meaning, class, let me just simplify that one, that if there is 1% change, okay, if there is a one increment change in the consumption of x sub 1, the total utility, class, will increase by this much. Okay, so here nx sub 1 plus 2x sub 2 multiplied by dx2. This is just the marginal utility of x sub 2. So meaning, class, that if we increase our consumption of good x sub 1, total utility will increase by this much. Okay, so well, let me just correct myself here. This should be du here because we're getting already, right? So we're getting already the total differential. Okay, so in this case, du now represents the total approximate change in utility when there is a change in x sub 1 and there's also a change in x sub 2. Okay, so I hope you can see already what is happening here. Now, in partial derivatives, we're only allowing one variable to change. In this case, class, how again, allowing us simultaneously. So I'll just use the word simultaneously. So if we allow this one to change, if we allow this one to change, what is the total effect to that one in our dependent variable? Okay, question? So this case right here, class, the examples that we only provided in the earlier slides does not present us with a change in x sub 1. So in that case, or a change in x sub 2. So we just can we can just copy that one into our total differential. But it would be a different case pag may pag may change na tayo sa variables. Okay? But before I proceed to that one, I'll need to make sure that we have understood again somehow the basic or the fundamentals of total differential. Question? Before I proceed to giving a specific example for any of the changes in your variable. Okay, sige. If there is no question, I'll proceed. Now, Yung examples natin is, again, the first one, I think the first example is just getting any linear function, and then an economic application was utility function. Let's have an example from firm theory this time. Okay, so let me just okay, I'll just use here. Now let's use this one, and let's have a production function, which is again from our firm theory. Okay, so all right. Omengan, can I call you? What is our production function again? Omengan, what was our production function again in firm theory? Just a typical production function.
Hello, ma'am.
Hi, yes, go ahead.
For the production function po, ito po ba yung sa quantity equals the function of labor and capital po?
Yes, precisely. Okay, thank you. So this is again, as what Umengan mentioned, class. When we talk about production function, we are dealing now with two variables here. So Q is a function of capital and labor. Okay, let me write that. Okay, so again, we have two variables here. We again, Q here now relates to the output. Then we also have K here as our capital input. We also have labor there as our, or L there as our labor input. So we are, these two, again, these two inputs are necessary in order to have, or in order to, for us to produce a quantity or to have an output, okay? Now, let's also talk about, since you're only few class now, so probably I'll call you a couple of times here. Malabo, what is can you please provide us the partial derivative with respect to K here, or yeah, what is MPK and MPL here? Okay. What is MPK? So let me guide you, class. When you talk about MPK, that is just the marginal product of capital. Again, that is, you're getting the output changes with respect to capital, and you're holding L fixed. So what is MPK, Malabo? So MPK is okay. How about the others, class? Would like to, again, this is we're just doing the same exercise just like what we did last time. So yes, Mengan, can you just provide MPK and MPL? So let's start with MPK.
For the MPK po, that's partial Q over partial K po.
Okay. Since we're getting total differential, I'll just change slightly, quite slightly, huh? So that's partial F and partial. Go ahead.
Partial F, partial F po ba, ma'am?
Yes.
Partial F over partial K po.
Great. For a while, wait for me. So that's, let me just change this one. So that's MPK, partial F, partial K. And then, what is MPL?
For MPL po, partial F over partial L po.
Okay, good. All right. So also, I'll add, to make it more formal, class, that is when you have, thank you, Mengan. So for in that case, when you have, you're getting the marginal product of capital, you see that we're getting the partial derivative with respect to K. We're now holding L here fixed or constant. So we can also rewrite this as this one here. So that would be K and L here. Okay. And also do the same for MPL. So let's Now, again, in economic theory, what this implies is that MPK is the rate at which the output change with respect to capital. Again, here, and MPL here is the rate at which changes with respect to labor naman when we're holding again capital fixed here. So in this case, class, let's have a specific example. Let's have Cobb-Douglas production function. Let's use this one. This one. Right. So let's have this production function, which is again a Cobb-Douglas one. So let's have 4K. Let's have let me just check on the coefficient. So it's 3. Okay, let's have a Cobb-Douglas function, production function where the coefficients are equal to 1. So let's have 3 over 4. So let's have 3 over 4 and L over 1 over 4. Okay, so might want to help me with this one. So supposing with our Cobb-Douglas production function, Q is equal to 4 K raised to the power of 3 over 4, L raised to the power of 1, 4. So again, this is a Cobb-Douglas production function, which means to say that the coefficient should be equal to 1. So that's 3 over 4 plus 1 over 4, yeah, equal to 1. Let's also put some, let's also add to our given here. Supposing that our K here is 10,000, meaning we are, again, when I refer to K and L class, remember K here is R times K and labor is W times L. So parang that's rent times capital and then wage times labor. Okay, so you might find the figures a bit superficial, but again, I'm just taking it from R times K and W times L. So supposing we now have a K which is equal to 10,000 and we also have L which is equal to 6,000. No, let's have 625. Okay. Now, with that one, okay, who would like to give me, who would like to provide for the class the total output given those figures? What's total Q class? What's Q here? So when you have a production function that is equal to 4K raised to the power 3 over 4 times L raised to the power of 1/4, and you have the specific units here where K is equal to 10,000, L is equal to 625. What is output equal to? Anyone who would like to raise their hand? What is Q is equal to? Let me also do my own calculation here. Yeah, so that is, what is the answer? Okay, probably we can do it together, class, so as not to be fully into the class. So what's the answer, class? Actually, have not got the answer yet. What's the answer? Yeah. What's the answer here? Okay, who has the answer? But we can move forward. What's Q equal to? Okay, who would like to raise their hands? Atiga? I have not heard your voice today. So what's our Q, Atika? Okay, how about the others, class? What's Q? Sige, let me know if my answer is correct. Is this correct? Is this correct, class? Did you get 15,000? Okay. Alright, sige. Let me this one we had the same exercise before. Okay, so let me ano na lang. Okay, so eto, yeah, let's okay, so again, we have your production function class. All you need to do is just to substitute the values that you have. So for example, when you have K as 10,000, you just have to substitute 10,000 into the production function. You also do the same for L, which is 625. So it would be it would look like this. Okay. So in that case, Q would be equal to 4 times 10,000. Again, 10,000 is K here. Raised to the power of 3 over 4 multiplied by 625. 625 is our labor raised to the power of, which is 1 over 4. Okay. No, we're not doing total differentiation, total differential yet. No, we're still getting Q here. So, which means to say that Q is equal to 20,000. Okay, so I have not yet asked the total differential of Q, but rather I asked what is output. Okay. I also thought na bakit natagalan? No, we're only doing we're only getting Q, no, you're getting too excited, but that's good. It might it reflects your that's good. All right. So again, let's go back to my question, class. No, I only asked first to get Q here. I did not ask you to estimate Q, or I did not ask you to provide me the total differential. Kasi again, we have not made any changes here. Ang sinabi ko lang na K here, we're starting off with K with having 10 units, 10,000 units, and L starting as 625. So, diba class, when you're talking about total differential, it means that you're getting a change. So we're comparing two values here. So in this case, we're not yet comparing, we're not yet allowing any change at all. Okay, so we're just first starting with just getting Q here. Okay, so that's good. That's good. Okay, so again, let me just correct, that's total differential. Okay. The word is total differential. All right. Now, again, do we have a question, class, on what these figures mean? Do we have a question? How did we arrive with 20,000 and not 15,000? None? All right. Okay. So again, if you're confronted with this problem and then you're asked initially what is the output for Q, all you have to do is again to substitute. Okay. Now, what happens after class is that supposing I'll tell you, okay, how about if we allow a change in any of these variables K and L? So in that case, that is a hint for us to now get the partial derivative of these the partial derivative with respect to any of these inputs. So in that case, let me just get this one. Okay, and then we'll do this. Put this one on the side. Okay, all right. So I'll put the given on the side here so that we can maximize the space. So again, total differential. I keep asking the same question. How do we get total differential now? For a while kasi. Okay. Let's first, since we have figures anyway, let's try to get MPK here. Okay. So I'll do MPK and I'll ask one of you to do for MPN. Okay. So let me just check on that one. So this one would be partial Q. Okay, so on your end there, you can get, since you already have a production function here, you can get MPK on your end. Okay, so that's MPK. So that's partial. Now we can just say it's partial Q, partial K, because again we have a production function. We now have a function here. Okay, so that's partial Q, partial K. Okay, let's Q here. Okay, so let's also add the units. So that's 10,065 equal to, for what was that? It's 3. Okay, so while waiting for me, again, you can get your own MPK there. Okay, para lang hindi masayang oras natin. So that's 3625 raised to the power of 1/4. 1/4, and then, so this is 10,000 raised to the power of 1/4. Okay, and that's 3/5. Okay, here, let me just, okay, so here's our MPK here. Okay, here. So here's our value for MPK class. Again, this is and this is just this is I would say the entire picture when you're getting MPK, because again you already have the values here. Unlike what we did with our first with MUX, which is again any utility function, we stopped to a point again just by getting this kasi we don't have values for any of these x1, x2. The case for the production function class, and specifically for this example, we have values for K and L. So we can really get the value for MPK. Okay, so let's take a first look on what we did here. So again, our definition of MPK states that it's partial F partial K multiplied by KL. So in that case, because we now have again our production function, which is equal to this one, we can just get partial Q, partial K. This is supposed to be, let me correct this one. This is again, partial K, partial Q, partial K multiplied to K and L. Again, KL here is 10,000 and also 625. Again, you can also substitute this one. So ang nangyari dito class is that okay, I'll delete this one and I'll give you a complete picture. Kasi I don't want. Let me just give you the complete picture here. So it's perfect. Partial K. Okay, for a while, 625 partial K. For a while, let me just complete the picture first kasi I went straight to the end of getting the answer. Where am I? So that's 3/4. Okay. So that's 3K. So that's 3K. Okay, I'm actually starting on the first one class because I went straight So that's okay, so that's raised to the power of negative 1/4. To the power of negative 1/4. We're holding, okay, and then we're holding on constant. Okay, all right. Let me just take a quick look muna. So that's MPK. We're holding L constant here. So that's 3/4 times 4. So that's 3 multiplied by K raised to the power of negative 1/4 times L/4 times KL here. Okay. Are we good in this part, class? I am still discussing this one. Are we good in this part? Okay, so again, this is our MPK here. Now, the next thing that I did or that we did was because this is a negative 1/4, we can just put this one, we can make this one as a positive, make this one a positive exponent. So we bring that, forgot the technical term, but again, we can just bring this one to the denominator. And that's why we have 3 times L/4. Let me just complete this one first, para you would know what I'm talking about. So that's 3 times L/4. And then we have K raised to the power of 1/4. Okay, so ito yung nangyari. Here. So let me also. Okay, here. This is probably the best, the complete one. So again, the first thing that we did was we get the MPK and holding L constant here. We multiplied it, or we put muna on the side K and L. The next thing that we did was again make this one, make the exponent positive in a sense. So we bring that one down. So that's now K over raised to the power of 1/4. So, which means to say, class, that our numerator now is 3 times L raised to the power of 1/4 over K raised to the power of 1/4 times KL here. Okay. Now, before we go into this one, do we have a question why this one was possible, or why we rewrote it this way? Okay, so rules of exponents, class. So we can just use it, or we can write it this way. Question about this one? None? Okay. So again, this is our MPK. In usual practice natin, ang nangyayari is we just end up around this part, diba? Now, because we have values already, we can just go ahead and write it this way. Okay. So what happens next is that we just substituted the values. So that's 3 times L. Again, L is 625 over K. Again, K is 10,000. We can again write it this way. And so substituting all the values will give us 1.5. Okay. So that is our value for MPK. Again, class, sanay tayo na we're only given with a production function, and then we get partial derivative with respect to K or L. In this case, it's very specific. We have a value for K and L there, and so we got 1.5 as our marginal product of capital. Now, let's take 5 minutes of our time. Let's try to solve partial Q partial, this time MPL naman. Okay, so I'll put this one on the side. Okay, so right. Okay, so let's solve for MPL naman. Okay, so I'll pause the recording and then we'll take our time, probably 5 minutes of our time here just to get MPL. You can do the same process. Just have to make sure that you use the appropriate values. Okay, so we're quite late with the recording, but anyway, do you understand what I'm trying to relay? Again, when we talk about total differential, that is again the change in the dependent variable when you change any of these inputs here. So that's the approximation. Now, again, there are two answers here, class. The first answer is again just an estimate. No, because we have our values on the side. But again, if you have again, let's just add this one. MPK, this is MPL, DL. Okay, I'll just rewrite this one. Okay, so again, this is just an estimation, but if you complete the picture, class, again, rewriting all those, doing the same process as this one, you'll get around an approximation that is equal to this.
Ma'am, i-accept niyo po ba yung estimation na answer?
This one?
Oo, yes, ma'am.
Yes. Yes. I would be accepting it. Kasi, yeah. But if I would be asking you, class, you know, if I would be asking you the actual output, when I mentioned the let me rephrase my thoughts here. So this one kasi, class, this is 20,000 0.14998. This is the definition of total differential. Di ba infinitesimally changes? Yun yung talagang definition. When you go back to the definition of total differential, that is again infinitesimally small changes in any of y and x. So the whole point of total differential, class, is getting at most the actual value when there is any the changes. So this one here is just again telling you if you're in the actual path of getting a good estimate. Okay, so but anyway, the most important thing here is getting this approximation, kasi that's how we define total differentiation. Okay, so again, this is just a shortcut for this one is just a shortcut version. Okay, so I think I will I'll just need to stop at this point, class. I'll give you an assignment. Okay, so again, this is it's up to you if you will do this one, but I probably would add that one to your third problem set. So as an assignment, class, let's have kasi we're constrained with time. So supposing scenario 2, okay, let me just change some stuff here. So supposing DL, again, this is positive 10, di ba? Kanina, we did positive 10, meaning we add 10 units to capital. What will happen if this is negative 2? Meaning that, okay, for a while, let me see. Put this one on the side. And what was our value again? So that's Q is equal to yung values natin, class, was 10,000. Supposing that we are reducing our K there, so that K would be 623. Okay. Okay, so as an assignment, or again, it's just an added incentive for you, class, to work on, what is the approximation of Q? You can both provide me the estimate. It's a bit class, no? You might be parang I'm making my own definition. But anyway, you can give me an estimate. Let's just call this one an estimate, yung eto. And we call this one the actual approximation. Okay, So for your exercise, again, as an incentive, you can provide me both the estimate and the approximation when we decrease our labor to 2 units. So there is negative 2. Okay,
Constant po ba yung capital, ma'am?
yes, good question. Let me also complete this one. We are holding capital constant here. So we're only allowing L to change. So that's why this is K is still 10,000 here and L is 623, meaning we've only allow 623, we're only allow labor to change. Did I answer your question, Kawano?
Yes po, ma'am.
Right. Thank you. Which gives me another idea, class. Okay, so let's have scenario 3. So scenario 3 will have, okay, so scenario 3, taka lang class. So scenario 3 is you both allowed the change to happen. These two inputs to change. So, di ba I mentioned last time na hindi natin siya itatakal kasi medyo complex. But because I think we have the capacity anyway to change. To have this one. Okay, so let's have this one. This is actually what will happen in the production mostly. So let's have this one as 10,000, 0.10. Okay, so scenario 3, what will happen, class, if you allow all variables to change? You allow K to change, that is, we added 10 units to K, and you also allowed L to change, meaning you deduct 2 units to the production. So you have 2 assignments. Again, it depends on you if you would answer it. I will probably add these incentives to your third problem set. So again, let me clarify my point. You will need to do scenario 2. Scenario 2 is, again, holding capital constant. You're only allowing L to change. Scenario 3 is you're allowing both variables to change.
May tanong po ako.
Yes.
Ma'am, yung MPK po ba, yun ba yung 1.5 times 10 or is it the 20,000?
Asan?
Ayan po, ma'am. Yung 1.5 times 10, is that MPK or DK?
Okay. 1.5 is MPK.
Okay, ma'am.
And then 10 is DK.
DK.
I'll correct myself. Thank you for that. This is supposed to be this one, and then also this one. Okay. Is that clear already?
Pero yung 20,000, ma'am, like, bakit merong 20,000 dyan kung wala naman sa formula?
Okay. This is our Q here.
Oh, okay. Tapos kapag may change na ng L, we just have to plus 20,000 pa rin ba or hindi na, ma'am?
Yes, kasi we're starting off with an output that is equal to 20,000. So again, this is only used when you're getting the estimate.
Oh, okay po, ma'am.
Okay, so as for MPL, just to give you an overview, so it's still 20,000, but that's already plus 8 minus negative 2.
Sige po, ma'am. It's clear po. Thank you.
Okay, so class, again, I feel to mention that I am doing 2 methods here. One method is just getting the estimate. This is just to give you, I'm doing a good one here where I'm in the same process. And this one is the whole process of total differential, meaning that eto na yung gagawin natin. Parang complete one na. Okay? When you are really using the exact values. Okay? So again, I'll just repeat. Again, I'm not really sure how many times did I mention that one. But anyway, for the second scenario, do it for L, meaning again, there is we have constant here as K. And then the third scenario, we're doing we're doing both here. So this is where complexity happens, class, and this is probably the closest one that we can get for as a real application in the production on the firms. So please take a photo of this one, of this.
Ma'am,
Yes.
ma'am, bakit po 10,000 po? Ito hindi po 20,000.
Sorry. What was that again?
Yung Q po,
Mm-hmm.
bakit po ma'am 10,000, hindi po siya 20,000?
Ito.
Opo.
This one is, let me write this one. So 10,010, this is K. And 623 is L. So yung question dito is, what is the exact Q when you allow change in L, change in K and L?
Okay po ma'am, thank you po.
Okay. All right. Other questions, class? Okay. Sige. I will probably upload the first part here of the when I'm done with my class, my 12th class. So you can just follow through later. Okay? So take note ha na hindi complete picture yung ginawa ko dito. Again, this is just the same with this one here. Okay, you can complete this one later on your free time. Okay, so if there are other questions, class, before we call it a day, we'll tackle elasticity later. Clarifications before I go? Okay, awesome, my question. All right. So if there's no other question, I'll see you all next week, Tuesday, to continue the discussion. Our discussion next week would be elasticity, and then we'll go to implicit function for chapter 8. So as you can see, class, chapter 8 is a bit long, but again, this implicit differentiation, you'll find this one a bit more comfortable because we can have just, there is a straight method for this one. Okay, so anyway, I'll be expecting your answers for next meeting, and that's it for today. You may already go.
Thank you po, ma'am.
Thank you ma'am.